a large cutting board is in front of us, and we know the following information. It's twice as long as it is wide. Twice as long as it is wide. And somehow, we're privy to the fact that its area, the area of the top, let's say, is 800 square inches. We know that, but we don't know how long it is, and we don't know how wide it is. So, based on the given information, since we evidently don't have a ruler with us to figure out how long it is and how wide it is, we're going to try to calculate that. So, let's let x be something. I'm going to suggest the width. We could let x be the length if you wanted to. Are you okay with letting x be the width? That'd be good? Okay. Let x equal the width of the cutting board. Draw the picture. Oh, it's too wide. There we go. And there. So x is the width. You can put the x on the other side too, but typically just one place, one of these two sides that have the same dimension is fine, because we're not talking about the perimeter, we're talking about the area. Then, don't want to stress anybody out here early in the morning, but if we let x represent the width, how would we represent a quantity that's twice the width? 2x, there we go. All right, so 2x is how we would express the length. So we have x, we have 2x. What's the formula for the area of a rectangle? Length times width. Area equals length times width. So we have the number for the area, 800 square inches. We have an expression for the width, we have an expression for the length, so we can substitute, and we have ourselves an equation, and I believe it is a quadratic equation, we'll see. 800 equals 2x times x. Just like that. So 800 equals 2x squared. Now to solve this, I'm thinking use the square root property of equations. First thing I notice about it is that it does not have an x term. That's a really good thing. It means it's much easier to solve the quadratic equation. What we want to do is isolate the x squared term, and once we do that, we can take square roots, apply the square root property of equation, and then we'll have the possible solutions and ultimately the one that works for us. So divide both sides by 2. I'm going to interchange the two sides while I'm at it. And divide both sides by 2. X squared equals 400. Now, if you wanted to at this point, I don't know if anybody would go this way with it, you could subtract 400 from both sides and factor as the difference of two squares. You could do that because 400 is a perfect square. But I would say no need to go to that trouble. X equals plus or minus the square root of 400. Square root property of equations there. X equals, since what we observed that 400 is a perfect square, that's plus or minus 20. Now, as far as the algebra of this goes, if we're looking for a value of x that has the property that x times 2x equals 400, there are two different values of x that make that happen. You can multiply it needs to equal 800, doesn't it? You can multiply negative 20 by negative 40, and that would give you positive 800. But it doesn't give you a rectangle, does it? It doesn't give you appropriate dimensions of a cutting board. So the negative 20 satisfies the algebra just fine, but not the geometry. Scratch the negative 20. Positive 20 should work a lot better. If the cutting board is 20 inches in width and twice that, 40 inches in length, the length will be twice the width, and its area, 20 by 40, would be 800 square inches. So that's what we need. It checks out pretty clearly, pretty quickly. 20, so how to say this, maybe something like this. Width, 20 inches. Length, 40 inches. Something like this. You could use a complete sentence if you want to. The width is, the cutting board has a width of 20 inches and a length of 40 inches, or just kind of fill in the blanks like this, and that accurately conveys the answer there. Another rectangle, a little bit more complicated setup than this. Not a whole lot more, but just a little bit more to think about. In the next example, sorry about that. The length of a rectangle is not twice the width, but it's 5 inches less than twice the width. So more complicated quadratic equation to solve basically is what's going to happen here. So another rectangle. And again, I'm going to let x equal the width. Then, how would you express a quantity that is 5 units less than twice x? 2x minus 5. So 2x twice the width, and then subtract 5 to indicate a quantity that's 5 units less than 2x. Common mistake there that we see sometimes in Algebra 1 would be to write 5 minus 2x instead of 2x minus 5. We just kind of think about what you're doing. You've got the quantity 2x, which represents twice the width, and then we're taking away from that to express something 5 units less than that. Set up the equation. Again, we have the formula for the area. Length times width equals area. So 2x minus 5 is the length. If we multiply that by the width, we get 33. Okay, this wouldn't make much of a cutting board, but maybe something like that. I don't know how big this thing's going to be. Let's see if we can figure it out. Simplify. A little bit more going on. We use the distributive property with the x there. 2x squared minus 5x equals 33. We have an x term, so we don't really have the option of using the square root property of equations. Instead, let's get 0 on one side. Right-hand side looks like the place for that 0, so subtract 33 from both sides. 2x squared minus 5x minus 33 equals 0. Now 2 just has a couple of factors. 33 has a handful, 1 and 3 and 11 and 33. So we might try just staring this down to come up with the factors. Kind of depends on your factoring skills. If you can kind of look and see and mentally rule out some obvious possibilities that obviously won't work, come up with the right negative and positive integers that when we FOIL or OI, we'll get the minus 5x in the middle. What do you think? You want to go with a negative there? Negative, so positive there. And are we thinking 1 and 33, or 3 and 11, or 11 and 3? 11 and 3, 11 and 3. We'll just check it by OIing. 6x minus 11x, yeah, that's negative 5x. Now the AC method is going to take longer, but it's a more sure method if you're sitting there wondering, how in the heck did they come up with that negative 11 and positive 3? Honestly, I'm kind of standing here wondering how you came up with that. I don't know if it's because I'm older and my brain doesn't work as fast as it used to, but I might have had to stand here and think about that for a while before I came up with those. But I would multiply the AC equals 2 times negative 33, and I would get negative 66. And I would say B equals negative 5. And I would look for two numbers I could multiply together and get negative 66 that had a sum of negative 5. And I could probably come up with those. Negative 11 is probably one of them. And positive 6. And then I would use the negative 11, since negative 11 times 6 is negative 66, and negative 11 plus 6 is negative 5. I could use those two, break apart the minus 5x, write it 2x squared. Let's go with plus 6x minus 11x minus 33 equals 0, effectively rigging up this trinomial into a 4-term polynomial, which can be factored by grouping. Factor a 2x out of the first two terms to get x plus 3. Factor a negative 11 out of the last two terms to get x plus 3. And then factor the x plus 3 out of each of these two expressions to get 2x minus 11 times x plus 3. I don't know. Is that just way more exhausting than absolutely necessary? Probably so. But if the negative 11 and the 3 aren't jumping out at you, it might be a way that you feel more comfortable going. It is for me personally, but I'll leave those factoring strategies to you. I'm going to give myself a little bit more space here. We've got it in factored form. We've got the 0 on the right-hand side. So let's set each factor equal to 0. 2x minus 11 equals 0, or x plus 3 equals 0. Add 11 to both sides. 2x equals 11. Divide both sides by 2. I'm short on space. What's 11 divided by 2? 5.5. There we go. 5.5, 5.5, or 11 halves. And subtract 3, subtract 3. X equals negative 3. Again, we see a number that satisfies the algebra. Think about what's going on with that negative 3. Now, negative 3 is a lousy width for a rectangle. But if we consider a quantity that's 5 less than twice that, what's twice negative 3? 9. Twice.
Wait,
Twice, well, 2 times negative 3. I should have said it like that. So negative 6, and then subtract the 5 from negative 6, and you get negative 11. So I guess maybe it sounds a little weird, but negative 11 is what you get when you take twice negative 3 and then subtract 5. Negative 6 minus 5, negative 11. What if you multiply negative 3 by negative 11 according to this formula for the area of a rectangle? Negative 3 times negative 11. There it is. You get 33. So negative 3 satisfies the algebra of this equation. But it's useless as far as the geometry is concerned. So scratch the negative 3. We don't want that. $5.5 is all we have left, so let's hope that works. Let 5.5 be the width, and now we need a quantity that's 5 units less than twice 5.5. What is twice 5.5? 11, and then 5 units less than that would be 6. All right. So figure not to scale, obviously. This is almost a square. 5.5 by 6, where it should be. 5.5 times 6, I'm guessing that's 33. Yeah, 33. So that is our rectangle. The width gonna be 5.5 inches, and the length 6 inches. A little bit more going on there than a situation where the length is exactly twice the width. So good one to practice on. This one is not in the notes. I included this one because it's an ALEKS problem. You'll run into this. Has anybody done the 1.5 ALEKS stuff yet? 1.5, did you run into this one? It's there. It's kind of like the discriminant problem, except it's not asking us for the discriminant. It's a projectile motion problem. A ball is thrown from a height of 141 feet, but it's not thrown upward. It's thrown downward. Initial downward velocity of 21 feet per second. So so when you look at the equation, it's the negative 16t squared, like we saw a little bit ago, but instead of plus some number times t, if it's being projected upward, like the arrow is being shot upward, this is being thrown downward, and the vertical component of the initial downward velocity is 21 feet per second, so minus 21t is where that comes from. The initial height of the it looks like a building there, right? Doesn't say, but that's what I'm inferring from the picture. The initial height of the ball as it's released is 141 feet above the ground. How long after the ball is thrown does it hit the ground? Well, key question here, and we've got to get it settled right at the beginning here. How high is the ball when it hits the ground? At the instant it hits the ground, what is its height above the ground? 0. That's key. It sort of goes without saying, but we have to go through that thought process. So what we want is the value of t, and we're not considering bounces here. So I'm just wanting one particular value of t when it hits the ground when h equals 0. So the quadratic equation to solve is 0 equals 141 minus 21t minus 16t squared. And that is sort of like standard form, but not really. I'd like to have the t squared term first, and then the t term, and then the constant term. If you wouldn't mind having the coefficient of t squared positive, really not all that necessary unless we're thinking about factoring it, but it's nicer to have a positive number. We're going to use the quadratic formula here, so there'll be a 2a in the denominator. It's probably better to have 32 in the denominator instead of negative 32 in the denominator. It's just a little cleaner, neater way of approach. So I'm going to not interchange the two sides, but I'm actually going to add 16t squared to both sides and add 21t to both sides and subtract 141 from both sides to get 16t squared plus 21t minus 141 equals 0. Don't even want to think about factoring this. I don't. I doubt that it can be factored. And if it can, that's just a place I don't want to go. Let's go immediately to the quadratic formula with a equals 16, b equals 21, c equals negative 141. So t, that's our unknown. T equals the opposite of 21 plus or minus the square root of 21 squared minus 4 times 16 times negative 141 all over 2 times positive 16. Now, if we were to calculate the discriminant at this point, I think we would find that there are going to be 2 real solutions to this equation, but I think only one of them is going to work for us because we need the time to be positive. It's not going to make sense to go back in time for this particular example. We're going to need the time to be positive. So let's see if we can get at least one positive solution. Negative 21 plus or minus the square root of, goodness, 21 squared minus 4 times 16 times negative 141. Suppose I might have used parentheses around the 16, but that really, the 1 does matter. Enter. So you get 9,465 for the discriminant. It is positive. So this quadratic equation does have 2 real solutions. We're hoping for a positive one. T equals, well, just like I didn't want to think about factoring that, I really don't want to think about simplifying this radical. I'm thinking it's about time to write down, I will write them separately, negative 21 plus the square root of 9,465 all over 32. And we'll punch that up on the calculator, see what we get. T equals negative 21 minus the square root of 9,465 all over 32. And we'll punch that one up on the calculator, see what we get. The second one I think clearly does not work. Both terms in the numerator are negative. Negative 21 minus the square root of 9,465 is certainly going to be a negative number. If we divide that by positive 32, it'll give us something negative. The other one, I think, has a shot at being positive. oops, negative 21 plus the square root of 9465. Get out from underneath the radical sign, close the parentheses, divide by 32, enter. How many decimal places? It says the nearest hundredth. So if I'm rounding this, if I'm rounding that, I'm going to say 2.38 seconds. T is time. You might check it. You might substitute 2.38 for T and see if you get 0 or something close to 0. The other one really doesn't help us, but if we press second entry and then change the plus to a minus, it is negative 3.70, but that's no good because we need a positive time when it hits the ground, so 2.38 seconds. Might be time to warm up or dust off. Well, I guess we've been using the calculators, but maybe look at the graphing capability of the calculator. Here's one where it's going to be more than just the standard viewing window, whatever that is. We'll need to manipulate the viewing window and see if we can get a good idea of what's going on with the graph. So let's take a few moments to look at this. So we know where the on button is. Do we know where the Y equals button is? In the upper left, right up here, if you press Y equals, the screen should look something like this. Does your screen look anything like this? Now, the 4 different modes the calculator can be in that determine what the screen looks like. The default mode, or the one fresh out of the box, is function mode, and that's the one we'll keep it in all semester long. You can take pre-calculus, trigonometry, calculus. There are other modes that you'll explore. But college algebra, we'll keep it in function mode. Y equals. Now, maybe it's not best that I start this off with something that's a function of t, because the calculator really would prefer x. So let's go with 16. Now, I want the calculator to display an x. It's really, there's another mode that involves a t, but we want it to display an x here. So for the, you know what? I need a negative 16 there. There's a negative sign and there's a minus button. Let's begin with the negative sign, 1/6, and then I'm going to press the button. It's right below the mode button. It's right above the, I guess to the left of the stat button. It has an X, a T, a theta, lowercase Greek letter theta, and a lowercase n there. I like to call it the XT theta n button. If you press that, and the calculator is in function mode, it will display an X, and that's what we want here. So negative 16, and then press the XT theta n button to display an X, and then minus, oops, sorry, goodness gracious. I need to square that X. So I'm going to press the exponentiation button. You can press the x squared button and you get by with that. But I'm going to press the exponentiation button, and then the 2, and then press the right arrow to get off of the exponent. So negative 16x squared minus 21x plus 141. Now, in order to see a simulation of the path of this ball that's thrown downward, I need a viewing window where the x goes at least as far to the right as 2.38. We might go a little farther than that. And the y, which indicates the height of this, goes at least as high as 141 feet. So I've just pressed the window button. You press the window button, and you see some numbers up here. My x min, I'm going to start at 0, and that represents time. 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. It's going to be on the ground before 4 seconds. So let's say the X max is 4. The X scale, let's make it nice. 1.57 is not nice. Let's make it 1. So set the X scale equal to 1. So when you see little tick marks on the bottom of the screen, that designates 1 second, 2 seconds, 3 seconds, 4 seconds. The Y min. Now we could set it, and I probably should set it to 0. I think I will. That'll represent ground level. Y is the height is 0. So Y min equals 0. Now the Y max, I'd like to see it from the beginning of its flight down to the bottom, so at least 141, 150, 160. I just want a little bit above that. Let me go 200. Let me go 200. That's probably more than I need. But 200 and a Y scale of, I'm debating, if I go 10, every 10 feet, 10, 20, 30, 40, 50, that's a lot of tick marks. It might not be too many. Do you think 25 feet? Let's go 25 feet for the Y scale. So you see the tick marks: 25 feet, 50 feet, 75 feet, 100 feet, 125 feet, and so on. If I press graph, let's see what happens. There we go. So it is the time that passes, and for any point in time, it indicates the height. Now, to evaluate a function like this, there's a pretty quick procedure that the calculator has for doing it. Several different features we need after we press the second button. So press the second button, and then where you see the trace button in the upper right, after pressing the second button, press the trace button, and it'll actually execute the calculate feature. So second, calc, and you get a menu. We will use probably 5 of the items on this menu in the next class period or 2. Number 1 on the list is one I want right here. Second calc value. So enter 1 for value. And basically, since X represents time, we can input a time and it'll tell us the height at that time. If we input 0, it says at time t equals 0. At the instant the ball is released, it's at a height of 141 feet. If we let 1 second tick away, though, let's type the 1. I don't go through the entire procedure. Second, calc, value. Again, just type a 1. A second after it's released, it's fallen, what, 37 feet? Did I do that subtraction correctly? I'm not sure. Whatever 141 minus 104 is, maybe that's 37 or close to it. It's fallen about that many feet, and it's now at a height of 104 feet. If we let another second tick away, gravity is taking charge and speeding up a little bit. It falls even further during the second, so that at the end of the second, it's only at a height of 35 feet. And then, after 2.38 seconds, it's pretty darn close to the ground. 0.3896, something like that. And it's going reasonably fast. Is that what you got? Something close to 0? 0 point, like half a foot above the ground. So it's not going to take long to cover that final half a foot, 0.3896 feet, to hit the ground. So some simulations here. Now, not actually using the equation solving capability of the calculator, but just kind of illustrating how we could visualize this using the calculator. We'll use the calculator next time actually to solve an equation. Let's look at hopefully one more of these. Oh, keep going back there. I just don't know if I want to do the latter problem. Let me do the lidless box problem instead. Lidless box, and actually I want to do the GeoGebra version of the lidless box because we get a little bit more from it. If you have the printable notes, I think you can change the numbers just a little bit from the printable notes and use this problem instead, the lidless box problem. An open box is to be made from a square sheet of cardboard by cutting a 4-inch square from each of the 4 corners. Assuming the box is to hold 49 cubic inches, find the side length of the square piece of cardboard to be used. All right, so great big piece of cardboard, something like that, square cardboard, flattened out, and we're going to cut squares out of this square piece of cardboard, like that, and like that, and like that, and like that. Now, from there to there, the cardboard, well, you want it to be big enough. So this is going to work. How big? I don't know. I'm going to say X. I'm going to say it's X by X inches. That's how big our sheet of cardboard is. And out of that, we're going to cut 4 by 4 inch squares. 4-inch by 4-inch squares. And then we're going to, I don't know what we're going to do with those little 4 by 4-inch squares that we cut out. Hopefully find some other use for them, nice craft project, something. But then we'll fold up these flaps and we'll make a box out of it. So the box will look something like, well, this, maybe, that. Something like that. We would like the volume of that box to be 49 cubic inches. Anybody know the formula for the volume of a rectangular box? Length times width times height. Basically the 3 dimensions, we multiply those together and that's what we get. Now we need to express each of those dimensions in terms of X. I think a couple of them, well, no. One of them is going to be 4. When we fold it up, the height of this box is going to be 4 inches. So that's one of the dimensions. The other one is the distance from there to there, and I believe it's the same, although the figure is not quite drawn to scale, as the distance from there to there. If we have the X and we take away 4 and we take away 4 again, what do we have? I believe it's X minus 8. Is it X minus 8? I think it is. X minus 8. I'm worried about my GeoGebra worksheet there. No, there's an X minus 8 there, so we're good. So that's X minus 8. That's X minus 8. So this is X minus 8, and this is X minus 8. And we've got our 3 dimensions. Length times width times height needs to be 49 cubic inches. And so X minus 8 times X minus 8 times 4 needs to be 49 cubic inches. Now ordinarily, I think if the X minus 8 and the X minus 8 were different instead of the same, I would probably FOIL those. Distribute the 4 across the parentheses, subtract 49 from both sides, and think about factoring this, or using the quadratic formula. But since they're the same, this actually lends itself really, really well to the square root property of equations. Because we've got a quantity squared and a situation where we can write this as a quantity squared equals a number. So I'm going to say X minus 8 quantity squared equals 49/4. What do we do next? Square root property. X minus 8 equals plus or minus the square root of 49/4. X minus 8 equals plus or minus 7/2. X equals 8 plus or minus 3.5 if we add 8 to both sides. So we're thinking X could be 8 plus 3.5, or X could be 8 minus 3.5. Now both of these are positive, but I'm not sure they both work for us. 11.5 or 5.5, this initial piece of cardboard that we have, if it starts out being 5.5 by 5.5, and we cut out 4, and then we cut out 4 again, in fact, I don't think that's possible. If it's 5.5 inches long and we cut out 4, we don't have another 4 to cut out. So I don't think 5.5 will work. Somehow that manages. I guess 5.5 minus 8 gives us something negative that we can square and get 49/4. It satisfies the algebra, does not satisfy the geometry. So scratch the 5.5. I think the 11.5 works. If we cut out 4 and then we cut out 4 again, it's going to leave us with 3.5 right there. And evidently 3.5 times 3.5 times 4. Did I do that? Yes.
How did you get 5.5 not 4.5? For 8 minus 3.5.
Oh. Oops. 4.5? Oh. Sorry about that. Still doesn't work. Yeah, I don't know. How would I grade that? You get the wrong answer and say it doesn't work. So 11.5 minus 8, that is 3.5, right? So 3.5 by 3.5 by 4. Okay, so it looks like it's 3.5. For the visual, there's our problem. There's our sheet of cardboard. I'm wondering how big to make that. How big do we end up making it? 11.5, something like that. So what we want to be able to do is cut squares out of the corners that are 4 inches. So we'll cut 4-inch squares out of that, and we want to have enough material left where we can fold up the corners and get a box that has a volume of 49 cubic inches. Well, if it starts out at 10.39 by 10.39, that's not going to be big enough. It's only going to leave us with a 22.8 something cubic inch box. But if we go bigger, if the side could be as much as what? How big did we say it had to be? Aha, there we go. If it's as much as 11.5 by 11.5 and we cut out the 4, fold up the sides, we get a box that's 4 by 3.5 by 3.5, and that gives us the 49 cubic inches that we need. So that looks pretty good. So the last one is section 1.5. The fireworks mortar. I'm going to go and warm up the calculator here because I want to look at a graphical approach at solving this. A fireworks mortar is launched straight upward from an initial height of 5 feet off the ground with an initial upward velocity of 144 feet per second. Write an expression for the height of the mortar. We'll denote the height by S. We could use H, but S works well enough. Find the time at which the mortar is at a height of 265 feet. And when will the mortar hit the ground in this idealized situation where we're basically neglecting the effect of friction as the mortar bumps up against molecules of various gases in the Earth's atmosphere. It's going to go up, it's going to come down, and the only force we're considering here is the force due to gravity. And we're assuming it's relatively constant, which is a safer assumption than the friction assumption, close to the surface of the Earth. So, okay, we'll work it twice. Once with the quadratic formula, and then again, graphically using the calculator, we'll confirm, hopefully we'll confirm or deny what we found out with the graph and calculator. So get that one ready when we need it. So we've got the basic structure of this, and this is not something that I'm going to ask you to memorize for the test. It was given, I believe, in a previous problem. In fact, let me go ahead and look and see. This will be given to you, this negative 1/2 gt squared plus v sub 0 t plus s sub 0 using 32 feet per second squared for the g. And since this is in feet, and the initial velocity of 144 feet per second and initial height of 5, so this information will be given. It's not a physics class, so this is a formula that I do not expect you to memorize. More than likely, what you'll see is S equals negative 1/2 times 32 t squared plus 144 t plus 5, and simplifying just a little bit, negative 16 t squared plus 144 t plus 5. If we substitute a number of seconds for t, square the t, multiply by negative 16, multiply the 144 by t, and then add all those numbers together, what it will do is give us a fairly decent estimate for the height of that mortar t seconds after it's launched. Yes? The 32 is given. It's determined by experimentation, and it's a constant. If once you define what a foot is and what a second is, and then you drop stuff in a vacuum and you calculate the acceleration that gravity has on them, you come up with if an object is dropped, its velocity is going to increase by about 32 feet per second each second. So it's a constant that you basically learn in physics class or through experimentation, but it's going to be given. So it's always 32. If we're dealing with meters instead of feet, it's going to be 9.8 meters per second squared. But the numbers are usually nicer in math class if we use the 32 feet per second. So that's the one that you can expect more than likely on the test. So, but that doesn't have to be memorized either. It's a great question because it's not at all obvious where that comes from. We'd have to get up on the roof and drop some stuff and get a stopwatch and time it and do some experimentation to come up with the 32 if we had to. But the 32 will be consistent from problem to problem. Okay, so this is 1 right here. 1, write an expression for the height of the mortar S in feet. 2, find the times at which the mortar is at a height of 265 feet. So the known is the S, the height, 265 feet. So I'm going to substitute 265 for the S. The unknown, and looks like unknowns, 2 different unknown values of t. It's t, negative 16 t squared plus 144 t plus 5. Well, we've got a couple options here. One option, ordinarily, I would like a positive coefficient of t squared. So I would think maybe add 16t squared and subtract 144t and subtract 5. However, when we solve this graphically in a little bit, I'm really going to want to graph the y equals negative 16t squared plus 144t plus 5. So instead of doing that, I think what I'll do is just subtract the 265 from both sides. That'll give us 0 on one side. I think that's minus 260 there. That'll give us 0 on one side, and we'll be able to use the quadratic formula. Now, it would be better if we could factor out a common factor here rather than having to substitute negative 16 for A and 144 for B and negative 260 for C, because that gets ugly. We substitute 144 for B and we square that. Now, if we keep track of what we're doing and we're careful punching buttons on the calculator, it'll probably turn out okay. But if we could factor out a common factor of 2 or maybe 4, or maybe even better than that, I'm not sure, 2 and 4 and 8, in fact even 16, it's a common factor. The first two terms, which of those will work for the 260? Is 260 divisible by 16 by any chance?
No.
Ooh, that's sad. How about 8? Is it divisible by 8? How about 4? It's got to be divisible by 4, right? Yeah. So, if we factor out a 4, we'll have 0 equals. Actually, I'm going to factor out negative 4. Good opportunity so that we're dealing with the positive coefficient of t squared when we substitute into the quadratic formula. It's not a must, but I think it's a little nicer so we don't have to deal with a negative number in the denominator. The a is in the denominator. Let's factor out a negative 4, and that'll be positive 4t squared minus, we factor out the negative, whereas previously we had a minus plus minus sign pattern on our trinomial. Inside the parentheses, it's going to be a plus minus plus. So minus 3016 plus, we said that goes 65 times. So it's going to boil down to finding the solutions. If we can set negative 4 equal to 0, we get nothing out of that. So it's going to boil down to finding the solutions of 4t squared minus 36t plus 65 equals 0. Maybe a couple solutions. Because the idea is the projectile is launched from, well, not high above the ground, maybe 5 feet above ground level. It goes up, it comes down. Now, it said straight up, but what I'm trying to do is indicate the passage of time, not so much the mortar moving away from the launching pad. I suppose that there's a human being at the launching pad. That human being needs to move if it actually went straight up. But it goes up, and the hope is that at a couple of points in time, t equals this and t equals that, it will actually be at a height of s equals 265 feet. And so we're looking maybe for two solutions to this. Hopefully there's at least one, but maybe two solutions. Real values of t that make this happen. So need more space. Using the quadratic formula with a equals 4, b equals negative 36, and c equals 65. Scoot that down and probably be good since it's a new page if you're printing that out. You can have that there at the top of the page for reference. So t equals the opposite of negative 36 plus or minus the square root of negative 36 squared minus 4 times 65 all over 2 times 4. So the two spots in the quadratic formula where there's a b, we substitute negative 36. The two spots where there's an a, we substitute a 4. In addition, we have the 4 that comes with the quadratic formula, and then 65 goes where the a was. Wonder what we get if we take negative 36, and if you're doing this with a single sequence of keystrokes on your calculator, it is important to enclose the negative 36 in parentheses when you square it. Now, if you just realize that squaring negative 36 gives you the same thing as squaring positive 36, then you can just maybe not type the negative. But if you type the negative and you don't enclose it in parentheses and you square it, it'll give you the opposite of whatever 36 squared is. So enclose it in parentheses and then subtract whatever 4 times 65 is. And this will give us, what's the number underneath the radical sign called? It's, well, up underneath it, the radicand. Yeah, I guess in general it's called the radicand. When it's in the quadratic formula, what's it called? Discriminant. The discriminant, absolutely. So the discriminant is 256 in this case. And I don't know that I'd expected it to be a perfect square. When it is a perfect square, the problem said use the quadratic formula, so I shouldn't be terribly disappointed here. But when it's a perfect square, and I'm using the quadratic formula, I'm thinking, oh, if I'd have just tried a little harder, I probably could have solved this by factoring. Because we're not going to have radicals in our final answer because the square root of 256 is 16. So the radicals are going to be dealt with, and we'll have rational solutions here. 36 plus or minus 16 all over the square root of 8. All right, quick show of hands. Don't shout out the answer, but who knows what 36 plus 16 is? Yes. Who knows what 36 minus 16 is? Yes. So you wouldn't want to take 36 plus or minus 16 all over 8 and put a box around it and call that your final answer. There's some obvious simplifying that can be done to that. T equals 36 plus 16 all over 8, or T equals 36 minus 16 all over 8. Now it remains to be seen if I'm going to be able to carry out this subtraction, but I'm going to give it my best shot. Oh, the addition and subtraction. 36 plus 16, that's got to start with a 5. Maybe 52 over 8. And 36 minus 16, that's a nice one. 20 over 8. And then simplify. 52 over 8 is 26 over 4, or 13 over 2, or is that 6.5? 6.5 there. Or T equals 10 fourths, 5 halves, 2.5. 2.5. So two different real values of T, two different real times when the mortar is at a height of 265 feet. And I'm thinking the first one happens on the way up. 1 second, 2 seconds, 2.5 seconds. It's reached a height of 2.5 feet. And then it keeps on going up. At some point, it stops going up, starts coming down. The clock's still ticking. So evidently, 4 seconds after it first reached the height of 265 feet, it is again at a height of 265 feet, but this time on the way down, and then it continues downward. Perhaps the next question is going to be, how long does it take to hit the ground? But two different times when it's at a height of 265 feet, once on the way up, another on the way down. So to answer that question, let's say answer. The mortar reaches a height of 265 feet. Yes?
Back at the top, what do we do with the 0 equals -4? Do we just discard that?
Oh, yes, just discard it. Right here, I didn't mention it, but officially I'm using the zero product property. Because I've got the product of -4 and this trinomial equal to 0. So set them each equal to 0, and as soon as we do that, we realize since there are no x's nor t's, no occurrence of the variable, and the -4 equals 0, that it doesn't make any contribution to the solution set, so just discard it at that point. Absolutely, yeah, good, thanks. I had intended to mention that, but did not. So it reaches the height of 265 feet. At t equals 2.5 seconds on the way up. And again, at t equals 6.5 seconds on the way down. There we go. So two different times during the flight, it reaches a height of 265 feet. And final question there, when will it hit the ground? And the when, I would imagine that would mean from the time it was launched. It's going to be in flight for how long? And then what's the stopwatch saying? At the moment it hits the ground. And we talked about this last time. First we have to decide how high above the ground will it be when it hits the ground. Goes without saying that at the moment it hits the ground, it will be 0 feet above the ground. So we'll substitute s equals 0 into s equals -16t squared plus 144t plus 265. Did I mess that up? You're wondering. No, 265 feet. What's the initial velocity? The initial height is 5. Yes, I did mess it up pretty badly. Sorry about that. The initial height is 5 feet. There we go. Yes?
Okay, but if we already know that it like took 2.5 seconds to get to that one height, and then, so couldn't we just add 2.5 to 6.5?
That turns out to be pretty safe. In our model here, where we're assuming that there's no friction due to bumping into molecules of gases and so forth in the atmosphere, it is safe to assume that it takes the same amount of time to go from the top to the bottom as it does to go from the bottom to the top, going up and going down different amounts, same amount of time. And it's also a safe assumption that, and we'll talk more about this when we talk about quadratic functions. We'll revisit this problem when we talk about quadratic functions, section 3.1. We can also assume, although there are other ways of finding this, that the time at the very top is halfway in between these two separate times that occur at the same height. Say if it happens 2.5 seconds, this is by the symmetry of the graph, 2.5 seconds to reach the height of 265 feet, and then 6.5 seconds, what's halfway between 2.5 and 6.5? 4.5? Well, I'm thinking maybe not a... What am I thinking there? If I add 2.5 and 6.5, I get 6, 7, 8, 9. It is 4.5. Wow. Why was I thinking it would be a whole number? I don't know. Well, I was wrong. 4.5 is 2 seconds away from 2.5. It's also 2 seconds away from 6.5. So 4.5 is the time when it reaches the top. So if we assume 4.5 seconds on the way up, that is from S equals 5. Ooh, my S's and 5s are indistinguishable. Sorry about that. It is a safe assumption, if we are neglecting friction, that 4.5 more seconds, it will again be at a height of 5 feet. And it's going pretty fast when it gets to a height of 5 feet on the way down. So just a tiny fraction of a second from the height of 5 feet to the ground. So 9 point, maybe less than 1, I think is going to be what's going to work for us here as far as a really good estimate. Let's see what the quadratic formula does for us. In fact, let's look at this graphically. I don't think I want to revisit the quadratic formula. So let's do two things. Let's graph this. Y equals, whoa, sorry about that. Back to function mode. Where has this calculator been? Goodness gracious. Y equals negative 16x squared plus 144x plus 5. You can get the calculator. Of course, you type y equals to get to this screen in the extreme upper left, y equals. And then to get the calculator to display the x, the t is used for a different mode on the calculator, but the calculator likes the independent variable of x when it's in this mode. Simply type the xt theta n button, press that, and it'll display an x. If you wanted to square it, either you can press the exponentiation button, the hat, the caret, whatever you like to call that, and then press 2. Or if you're just squaring and not cubing or raising to the fourth power or some other exponent, you can get by with pressing x squared after you press the x, and it will square it. For the window, how many seconds? Well, we're figuring 9 point something seconds, so let's go as far as 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds across the horizontal axis. The x scale, let's go with an x scale of 1 second. Y min, well, the y max, it's going to go, we don't know how high it's going to go. We know there are a couple points in time when it's going to reach a height of 265 feet. Maybe it goes 300 feet, maybe more than 300 feet. Let's go 350. Let's go with a y scale of 50. Never mind with the x res, I just leave it at 1 all the time. It never seems to hurt anything. And the y min, the only reason I would change the y min, I mean 0 might make sense. Maybe I won't change it. Maybe I'll just leave it at 0. There we go. So y min equals 0. And it should display a pretty good graph. Remember, it's not the actual path of the mortar, but it is the graph of the height versus the time that has elapsed. Graph. There we go. So to confirm what we have so far, you can press the, how are we doing with this graph? Anyone need help producing this graph? We are right out of the box here, so let me see if I can pause this and get everybody caught up, because this is vital. You want to be comfortable with getting the calculator to do what you need to do. I'm looking at. Find see what the window looks like. Window 10. That looks good. What happens when you press graph? Whoa. Oh, negative 16. You can, without overriding that, you can press second and then insert. And then down at the bottom, next to the decimal point, you can press a negative sign. 16. And then second, insert again. And put a 1 in front of the 6. There we go. And press graph. Excellent. Good. Anybody else have any questions about how to get the calculator to look like this? Display this picture. Next, went away. Next, you want to just confirm the values that we have so far. Second button followed by the calc button. Actually, it's the trace button, but it has the word calc up above there. So second and then trace is second calc. Number 1 on the list is value. If you just want to take and substitute in a value for the independent variable, like a value of x, which for us is time, press 1 and then substitute 0. It was given that at time t equals 0, when we click the stopwatch and fire the mortar, it's at a height of 5 feet. So that's where it starts. Then if we go 2.5, it's all the way up to 265 feet. It continues upward. 4.5 feet was our estimate of how long it takes to reach the top. And this is unfortunate, but I'm going to have to go higher here. Let's go 450. Because it was getting in the way of the text up there. Second calc value, number 1, 4.5. And it's at the top. Maximum height of 329 feet. We'll look at a formula for finding that in section 3.1. And then it's on its way down 2 seconds later at time t equals 6.5. It's again at a height of 265 feet. And we said 9 seconds. It'll be 5 feet above the ground yet again. And then it won't take much longer. It's going pretty fast. It's pretty close to its original velocity. If its initial velocity at t equals 0 is 144 feet per second directed upward, then again, neglecting friction, its velocity at time t equals 9 will be 144 feet per second directed downward. It's moving pretty fast. It's not going to take long to cover those last 5 feet, less than 1/10 of a second. So we'll see what it is. What we need, though, is a graphical approach at this. The simpler of the two graphical approaches to solving equations, I believe, is the intersection of graphs method, where basically we put 2 graphs on there and we ask the calculator to find the points where the 2 graphs intersect, and we use the x-coordinates of those points as the solutions. Those are the solutions. So I'm going to create a little bit more daylight in between the bottom of the screen and the x-axis. Let's say a y-min of negative 200. Now, if there's a big hole in the ground, it goes up, it's going to come down. It'll continue downward below ground level. Otherwise, it'll just stop, and the end of the mortar experience will be there at 9 point something seconds. So to see exactly where that happens, one thing we can do. How do I want to do this? I want to graph. It's going to look a lot like the graph that we had. I want to graph y equals this right-hand side there. Instead of, what equation am I trying to solve? I'm actually trying to solve s equals 0, aren't I? All right, so I'm trying to solve negative 16t squared plus 144t plus 5 equals 0. If we're trying to find where the thing intersects the x-axis, and that's what basically has to happen, we've got to look at this and we've got to figure out what's the x-coordinate of the point where it intersects the x-axis. What we want is the x-intercept method. Now we could use the x-intercept method in any case. Just the first step in the x-intercept method is to get 0 on one side. So you'd have to take everything on one side and subtract it from both sides and get 0. Here we already have 0 on one side. So all we have to do is graph y1 equals negative 16x squared plus 144x plus 5. And then we'll use second trace with, of course, the calc up above it. Is it 2? Second calc, it is 2. The 0 feature on the calculator. So because what we want is the value of x, or multiple values of x possibly, that make it equal to 0. What number can I substitute in for t and get 0 for s? So we're finding the 0 of this expression. So after pressing 0, it's going to ask for a left bound. If I successfully give it a left bound, it's going to ask for a right bound. And if I successfully give it a right bound, it's going to ask for a guess. So basically the left bound is a number that I think is a little to the left of where the x-intercept is. I can get that by typing in a number. I could just type in 8, enter, and it'll set that as the left bound. Now the right bound is a number that I think is a little to the right of what the x-coordinate of the x-intercept would be. I could type in 10. I have to be careful not to type in a right bound that's not between the x-min and x-max. If I type 11, it says it's invalid because that's not in the current viewing window. So if I redo that, second calc 0, type an 8 for the left bound, and then instead of typing something in, I'm going to press the right arrow multiple times until the cursor actually has an x-coordinate that's greater than where I think the x-coordinate of this 0 is. And so it's 9.46 something is what I'm officially using for my right bound. I'm going to press enter. And then for a guess, in case there's more than one x-intercept in that interval, I would at that point want to move the cursor closer to the one that I wanted to find first. But if there's only one, you could just press enter and use the 9.46 something, your right bound, as a guess. I don't want to worry anybody, so I'm just going to press the left arrow a few times until it's approximately on the x-intercept, and then press enter. And having done that, calculator searches and comes up with, wow, 9.03. 9.03 seconds. So just a little more than 3/100ths of a second to get from a height of 5 feet to the ground, traveling at a speed of 144 feet per second straight downward. And of course, it's continuing to accelerate, but it doesn't accelerate a whole lot in 3/100ths of a second. So t is approximately 9.03 seconds. So on the test, I'd like to see the graph just on your paper. Take that picture and copy it and scribble that. Maybe not scribble, but just as nicely as possible. Indicate there. Go ahead and indicate the point of intersection that your calculator finds to as many decimal places as I asked for. I think 2 is actually a bit much, but I'm going to go with 2 decimal places there. And then indicate the solution. So draw the picture. If you were solving using the quadratic formula, I'd expect to see the quadratic formula. If you're solving it using your calculator, I just expect to see the picture that your calculator shows you when you graph it. That's what I'm looking for. No quadratic formula necessary in that case.